Here is part 2 of lesson 3.3 for advanced functions grade 12. Example 2. We're going to find the domain xy intercepts, asymptotes, positive, negative intervals of f of x and also sketch this function. So once again, we're going to use the 4 features of quotient of two linear functions. Start with x-intercepts. So set your function equals to 0. You're trying to find the x value that makes this possible, and it is x equals to 2. Finding y-intercept requires us to evaluate the function at 0, so f of 0 tells us it's negative 2 over 4 or negative 1 over 2. Vertical asymptotes. Once again, this is where the function is undefined. So set your denominator 3x plus 4 equals to 0. Solve for x is negative 4 over 3. And last but not least, the horizontal asymptote. You can use the limit notation to find this horizontal asymptote, or using the shortcut. Remember, we said the shortcut is really y equals to the coefficient of x for the numerator over the coefficient of x in the denominator. So this turns out that y equals to 1 over 3 will be the horizontal asymptote for this particular function. The question also asks us to determine the positive and negative intervals of this function. So similar to the sign charts that you have made in the last chapter, you can look at this by, instead of looking at zeros, you can use the vertical asymptote to separate your two regions, because we know that this type of function or quotient of two linear function always add up with two branches, one positive, one negative. So x equals to negative 4 over 3 is your VA. So you're going to examine region that is less than x equals to negative 4 over 3, and also regions where x is greater than negative 4 over 3. You can also take your function f of x apart by looking at x minus 2 is numerator and separate that from 3x plus 4. So here are the two so-called factors. And then using test point, so pick a number less than negative 4 over 3. Let's say negative 10. So negative 10 minus 2 is negative, so that's negative. 3 times negative 10, negative 30, plus 4, negative 26. So that's still negative. But when you take a negative divided by a negative, you will have positive. And then we know that because x equals to negative 4 over 3 is your VA, the function will be undefined. And then a test point for the region x greater than negative 4 over 3. So you can pick positive 10, you can pick 0. 0 minus 2 is negative, and then 3 times 0 plus 4 is positive. A negative divided by positive is negative. And so we can use these information to help us determine that, well, here are my VA and HA, and the region to the left is a positive branch. It will sit above your HA, horizontal asymptote, and the branch on the right will sit below that. Okay. And then for the domain for this type of function basically only has one restriction, where you say x is not equal to negative 4 over 3, which is your vertical asymptote. Example 3. So we're trying to work backwards and play detective here. Write an equation for a rational function whose graph has all the indicated features. So you're given all the x-intercept, y-intercept, vertical asymptote, and horizontal asymptotes. So there's a bunch of combination of numbers. Some numbers are positive, some numbers are negative. So we have to do some mix and match here. Before we do mix and match, let's look at the general requirement, a general equation of, like, if I'm given a function y equals ax plus b over cx plus d, where do A, B, C, D go in terms of, where x-intercept, y-intercept, BA, and chase are. So for the x-intercept, we just go back to basics. F of x is equal to 0, which forces us to compare ax plus b equals to 0, or the x-intercept always becomes negative b over a. And then for y-intercept, it's f of 0. So if I submit 0 into this general equation, your y-intercept is always b over d. For the vertical asymptote, we know that we set the denominator, so in this case cx plus d equals to 0. So your vertical asymptote will always be x equals to negative d over c. And then for your horizontal asymptote, it will be the shortcut where y is equal to your coefficient of x in the numerator over the coefficient of x in the denominator, or a over c. So now if I compare these ratios of a, b, c, d's to these actual values of x and y and b, a, h, a, what can be done? Well, I'm just relisting everything without placing the negative signs with a particular letter or variable. And what catches my mind, or my eyes, are these two ratios in particular. I see that a and c is 3 over 5, so that means a and c must have the same sign, right? Either they're both positive or they're both negative. If I look at b over d, it is a negative ratio. It tells me that, well, b and d must have opposite signs, so one is positive, one is negative. And then you go back to the first two ratios that has more negative signs in them. Well, you just consider, well, usually our leading coefficients are positive. And because a and c both have the same sign, if I assume a is positive, so I have a equals to 3, well, then I'll have negative 1 equals to negative b, which forces b to be positive 1. Again, here I'm going to assume c is positive, so 5 is positive. It forces us to say that 2 must equal to negative of d, which makes d negative 2. So a and c have the same sign. Now, if we follow this, do b and d have opposite signs, like what we said earlier? And they do have opposite signs. Therefore, we can conclude that the function f of x should be 3x plus 1 over 5x minus 2. So this takes you to the end of this lesson. You can use the rest of the period to work on your classwork or homework found in this box here. I will see you tomorrow.